We just transitioned from talking about abstract algebra in the abstract, kind of, thinking about what algebra looks like when we don't necessarily have numbers and familiar arithmetic to do it with. We talked about how to use multiplication tables to keep track explicitly of how algebra works in a given system. We talked some about equivalence relations and modular arithmetic last week. And then the culmination of last week's exercises is that we came up with these three properties that a subset of the integers had to have. So let's get our minds back into this as a way to get started today. That we had an equivalence relation where two integers x and y were related together if and only if their difference, x minus y, belonged to a subset of the integers called a. So we defined x and y to be integers, and a is a subset of the integers. And we defined a relation in this way. Then this relation was an equivalence relation if. So what had to be true? What was the statement that you and your teams set forward to prove on the proof that we finished last Friday? What had to be true about the set A? First is that A has to contain the 0. A contains 0. And the role that 0 plays in the integers is, what is 0? What makes 0 special? What kind of an element is it? It's an identity element. Right. So we call that the identity property. Okay, so that was the first thing that we wanted to guarantee. What was another? The inverses property. And so what was the statement of the inverse property?
P is an element of A and negative P is an element of A.
Right. The only thing I would change there is the logical structure, where you said and. What I want is an if-then statement instead. So if P belongs to A, then what?
Negative.
Minus P belongs to A. Yes, very good. Cool. So that's the inverse property. A cannot have an element unless it also has the inverse of that element, right? And so every element has something that can cancel it. That's why we want the inverse property, because cancellation is a high priority for us. If we want to solve equations, we need to be able to cancel stuff away from the unknown variable, right? So we need everything to be able to be canceled. So we need the inverse property. And what was the third?
If P and Q belong, are an element of A.
If P and Q belong to A.
P plus Q
Then P plus Q must belong to A, yes. So this is essential for our simplifying expressions, right? That if there's some way for me to take two elements of this set and use the operation on the integers, which in this case is addition, and combine those two integers together, and if they fall outside of my set somehow, then my set's not a self-contained system. And what's the word that we use in place of self-contained for this property? Closure. This is a closure property. And so these were the three properties, each one of them aligned with one of the three characteristics for a relation to be an equivalence relation. Right? That A contains the 0 element guaranteed that this equivalence was reflexive. That the inverse property was satisfied by A guaranteed that this relation was symmetric. And that it was closed under addition guaranteed that this relation was transitive. Right? So each one of those three requirements for this relation mapped onto a property of the set A. Having done daily work number 5 before today, you now know that these are indeed the very three properties that are the ones that we want to take for granted in any system of abstract algebra that we do for the rest of the semester. And with these three definitions, we have now met the definition of the abstract algebraic object that will consume us for the whole rest of our spring semester. And that is a group. So, remind me, what is the definition of a group? So what data, what information do I need to specify a group? So every group begins its life as a set, and we call the members of that set the elements of a group. So consists of a set. And usually when the context is clear, we'll call that set by the same name that we call the group. A set of elements, we'll call the set G. But in addition to a set, what else do we need in order to talk about a group? an operation. We need both nouns and we also need verbs, right? We need things and we need ways of combining those things. And an operation. I'll just be real specific here and say it's a binary operation. It takes two of my elements and it produces an output. A binary operation dot, I'll call it, which is a function from G cross G into G. In other words, we feed it two elements of my group, two elements of this set, and it produces for me an element of my set. And usually, to make sure that we're clear about it, when the context is not clear, we'll refer to the group by this sort of ordered pair. We specify the set and we specify the operation. So G comma dot, right? And the combination of those must satisfy all four of these properties. Satisfying for all, let's call them X, Y, and Z in my set of elements, these four properties. And we have kind of sort of informal definitions of these properties from the context of the relation on the integers that we were talking about last week. But let's make sure that we have set down in stone what they look like when we're talking about an abstract group. So let's start, where can I start? Let's just go down this list, starting from the identity property. What is the abstraction of the identity property? What does it look like in an abstract group? How do we take this A contains 0 observation and make it abstract, take away the specifics of the integers in addition? How does the identity property sound in a generic group? Say again? All right, so we have this element E. So that means we also need to say where this element E comes from. But so E, this E, is going to play the role of our 0. And what property does it need to have in order to qualify as an identity? How do we recognize an identity when we see it, Casey?
Like E times G equals G. So
okay. E, so that it leaves things unchanged when it operates upon them. Here, when it operates upon them from the left, and then what about the right? Same thing. We want our identities to be two-sided identities. Okay. Here's a habit I want us to get into. This is also something we're going to talk about on Friday in our proof clinic. I've just written down two names, E and G, but I haven't told the reader where these E's and G's are coming from yet. Right, what do we know about these E's and G's? If I just write them down, it's not clear for which E's and which G's this statement is supposed to be true. Right? And maybe for how many E's and G's this is supposed to be true. So quantifying your variables before you introduce them in your argument is something I want us all to get in the habit of. So let me ask it first by asking, where are these G's coming from? For which G's does this need to be true? Yeah.
The elements in capital G?
The elements in my capital G, my set of elements of my group, right? And for how many of those elements does this need to be true? For all. So for all G's in the group, this statement has to be true. So I want to put that right at the front of my statement of the identity property. So I'll say, for all G in my group, I need this statement to be true. All right, how about E? Where does E come from? E also is an element of my set of elements, right? It's also in capital G. And how many E's must this work for? Ooh.
There is.
Okay, right. So all we need for the identity property is for an identity element to exist, right? We don't necessarily know whether there's more than one. That's a question I hope we can get to today. Such that, all right, so now I want to take a look at this assertion the way we've written it down here. For all G in my group, for all G in my set of elements, maybe is a better way to say it, for all elements G of my group, there exists an E, which is also an element of my group, such that this two-sided identity equation holds, right? That when E operates on G on either the left side or the right side, it leaves that element unchanged. How do we feel about this statement? I want to trouble the concept further. I would argue that we have all the right words written down. But the way that it's written down now, they're written in the wrong order. So I still have a problem with this. Does anyone see what it is? My point is going to be exactly what you said, that we want to write there exists E and G before we write for all G. Why? What's the difference? Why does it matter?
Because the E is consistently the same throughout G.
E is consistently right, that this element E has to be not just the identity for a particular group element G, it has to be the identity for all elements in my group, right? It's the same as, like, there's one spouse for every person versus every person has the spouse, right? Right. That's the difference. Like, if we put the for all G first, it means that you can come and hand me a group element G, and then I will supply you, here's the identity for that group element, right? But then I might be giving different people different identity elements. Right? Whereas if I first come to you and place an identity E on the table, and I say, this is my identity element, now all of your group elements have to satisfy this equation for that identity element. So the order in which we write these quantifiers matters. And we don't want every element, G, to have its own tailor-made, custom, bespoke identity. Right? That's not what we want. In fact, we want it to be just the opposite, that there exists an element which is the identity for all of the elements of my group. Okay. Let's turn our attention to inverse. Because now that we know that there exists an identity element, we need that identity element, actually, in order to define what the inverse property is. So how does the inverse property read? Maybe if we say that identity can be described as there's an identity for all elements in my group. There's an E that works for all G's. What's the statement about inverses? So, right, for inverses, the quantifier goes the other way around, because every element probably does have its own personal inverse, right? We're not going to have one element that is the inverse for all things in the group, probably. Yeah. Yes, each element has its own inverse. And so there, I agree, we want the for all G to come first. For all G, for all elements in my group, there is, and I'm not going to call it G inverse yet, I'm going to call it H. And how do I know that H is the inverse of G, or H is an inverse of G? What equation does it satisfy?
G times H equals E.
G times H equals E. That shows that H is the right inverse of G,
Which also equals H times G.
which also equals H times G because we want it to be the left inverse as well, right? So, right, that's, again, the logical difference between the orders of the quantifiers here, right? This identity element has to be the identity for everything. But this inverse is just the inverse of the thing of which it is the inverse, right? Every element gets its own inverse, but all the elements have to agree on an identity. Right? That's the big difference between how the quantifiers work there. All right, so those two are the trickiest because of the quantifiers. Associativity and closure go a little bit more quickly. How does a closure property sound when we write it down? So when we did it with the integers, here's how we said it. If P and Q are elements of A, then P plus Q is an element of A. How do we translate that into the abstract setting? Let me give you the hint here. That we'll start. What we had here was an if-then. I'm just going to change it into the quantified version, but they're logically equivalent. For all G and H in my group, what do we need to be true? Casey?
G times H.
G times H.
Equals, well, so some other element like F, and then F is an element of G.
Yeah, so if I call that something F, then that F has to be an element of G. Often in this definition, we'll dispense with the F and we'll just write G times H as an element of G, but whichever way you like it, right? So it has to be, anytime I combine two of my group elements together, their product, quote unquote, also needs to be a group element. So I can't leave my group just by using my operation. And then what about associativity? So this is one people stub their toes on a lot. Because it's not the same thing as commutativity. Right? Commutativity is about the order of group elements in a product. Associativity is about the order of grouping. So I take 3 elements, G, H, and K. What needs to be true? Yeah, Kenzie.
G times H in parentheses.
Yeah.
Times K equals G times H times K.
Yeah, there we go. That whenever I have 3 elements combined together in a triple product, that it doesn't matter how I group with parentheses the first pair or the second pair. I get the same result, whichever one of those 2 that I do. And associativity is important for a ton of reasons, one of which is that associativity guarantees that I can write that expression without parentheses at all, can unambiguously write GHK without having to put the parentheses, G times H times K, because then it doesn't matter if you decide to evaluate this first product first, I decide to evaluate that second product first, we're both going to come to the same answer. It also assures us that we can write things like G to the 10th power unambiguously. Because if I couldn't write G to the 10th power unambiguously, I would have a whole slew of different ways to evaluate G times 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 G times... I think I'm done. But depending on where I put the parentheses in there, if my operation is not associative, who knows what the answer is going to be? One of the problems I've been thinking about lately, I don't have an answer to yet, is I wonder if there is a group in which if I wrote down, let's say, G to the 6th power, if my operation wasn't associative, maybe there's a way to get 6 different answers. Maybe there's a way to get all the different elements of my group by evaluating G to the 6th power in different ways, right? Maybe. I actually don't know the answer to that. So when we sacrifice associativity, we sacrifice a lot. So it's a super important property. The good news is that it's a property, it's probably the least interesting property from my perspective that I want you to get in the habit of checking and verifying for yourself. Because one of the most important ways to make a group is to define this operation in terms of the composition of functions. Take the output of one function, plug it into another. An example of that is the symmetry group of regular polygons that we've already talked some about, right? Each of the symmetries is just a function. It's just a linear transformation of the plane, if you like. And because it's a function, composition of functions is always an associative operation. We could prove that, I suppose, if we wanted to. But since so many of our groups are defined in terms of function composition, associativity. This is a full list of the properties. These are the only properties that we're going to need. And we can get a whole rest of the semester out of these 4 properties. Our course from here forward sort of evolves in 2 major acts, I guess you'd say. You can maybe think of it as 3. But the first act is that we're going to really play in this sandbox for probably 3 or 4 weeks. Just getting our hands dirty with these properties and figuring out from this basic set of 4 things, what else can we deduce must be true for all groups, regardless of the concrete forms that those groups take. What do they all have in common? What properties? What is true of all of them just based on these 4 properties? We're going to get started on that today. And once we've done that, we're also going to, in parallel, be looking at sort of a variety of different examples, of which you've already seen a couple, right? The rational tangle group was the first example that we saw. The group of the symmetries of regular polygons we've worked with. That's going to be one of the really important examples of groups that we see this semester. We've also seen, indirectly at least, the group of integers where we add them with a modulus. So addition mod 12, addition mod 5. I'm also going to get you started this week thinking about whether multiplication mod 5, mod 12, mod 10 can make a group out of the integers as well. Also, a really important source of where groups come from is matrices, which actually we also saw an example, the 2x2 matrix example. But in general, we can also make a lot of different types of groups out of multiplying matrices. And of course, the numbers fields and number systems that we're accustomed to, like the real numbers, the complex numbers, the rational numbers, those all form groups under addition, variously multiplication sometimes. And so we want to take some time to really explore the breadth of sort of what are the most important examples of groups to study that can not only tell us something about those specific groups, but also to tell us something about the structure of groups in general. Probably the most important of those examples is the last one that we'll see before the midterm, which is the symmetry groups, not symmetry groups, symmetric groups, groups of permutations, groups of ways to rearrange finite sets of objects. Because it turns out that those are almost universal examples of what all finite groups can look like. We get a lot of mileage out of that. So that's sort of Act 1. And then Act 2 in the second half of the semester is, now that we've seen a whole variety of different catalog of types of groups to work with, what now can we say about the structure of groups in general? How do these 4 properties constrain what kinds of groups can exist in the wild? Okay, what is the full list of the types of groups that ever can possibly exist based on these 4 properties? That turns out to be a very challenging question. And yet, it's a question that has actually some pretty good answers, particularly if we restrict our attention to finite groups, groups that only have a finite set of elements. The question about what types of finite groups can exist was not completely answered by the field of mathematics until I was in graduate school. In 2004, I think, is when the so-called Atlas of Finite Simple Groups was published, which is essentially a catalog of here are all of the possible building blocks of finite groups that can exist based on these 4 properties and everything else we know about groups. So that's a very recent result that took a lot of very high-powered mathematics to come to bear. The question for infinite groups is still pretty open. Most algebraists study infinite groups from the standpoint of what's called representation theory. How can I relate my infinite groups to groups of matrices and linear transformations and things that we already are familiar with? If you came to yesterday's informational session for math programs, we heard from one of our recent graduates who is now working in representation theory in a PhD program up at Tufts. So those are the kinds of questions that he's tackling as part of his doctoral dissertation research. So it's kind of surprising we can get so much mileage out of this, but there is so much more to the theory of groups than even fits in our one semester. Again, there are still researchers studying group theory at every level of mathematics, so this is the beginning of a very long story.